Alright, so last time we talked about the addition reactions on alkenes. And the addition, two types of addition we discussed. Have we gotten it yet? Right, so the mechanism 6.9 is the section. Let me show you. So, mechanism 6.9 is the section here. And the insets actually gives you details of the mechanism. So the insets have a different number. The mechanism 6.4 and 5. That's what it is. All right, so we talked about addition to carbon double bond. And the two types of additions that we already talked about is addition of hydrogen and we talked about addition of hydrogen halide. X is a halide. And when you add hydrogen, of course, they come from the same side. We indicated that that's a syn addition. Whereas it's a different mechanism when you talk about a hydrogen halide, HCl, HBr, HI addition to a carbon-carbon double bond, because there it goes through a carbocation intermediate. And that's why they have a preference, and that's essentially indicated in Marconi cluster. Where the hydrogen is added to the carbon containing the maximum number of hydrogens. Now, the intermediary state involving the carbocation is also indicated by another indirect way in which we see rearrangement of products. And the rearrangement happens because of the generation of carbocation. An example of that is, let's say, if you have this particular alkene where you added, let's say, hydrogen fluoride, and it can be carried out at a very low temperature. The expected product, as we mentioned according to Marconi cluster, is a hydrogen would add on to the end because that has CH2 and this is CH. Therefore, a more number of hydrogens here, the hydrogen adds on there, and therefore chlorine would go here. So this is the expected product. But it's only formed at about 40%. And the 60% is actually a different product where we see that it is formed, chlorine is a different place. This is about 60%. So how did that happen? We can follow the mechanism and be able to explain that. Because in the very first step, you expect the hydrogen H plus to add on to the end, which would be the major. So you have CH3 now. And a carbocation is generated. And this carbocation can undergo a rearrangement where this is secondary cation. If it can become a tertiary, that would be the driving force. And indeed, that's what happens. Like you have a hydrogen here. The hydrogen, the hydride shift can generate another carbocation where this is now this carbocation, now this one gives you this product, and this one would give you the other product, which is formed because this is a tertiary cation. This is secondary. This is formed more than the other one. And so this is actually an indirect way of explaining the formation of carbocation, because otherwise you won't be able to explain the formation of this product. And of course there are other examples of similar type that was seen. Now moving on to addition that in addition to hydrogen halide, you can have other types of groups added to the carbon-carbon double bond. And one of the common one is the addition of water molecule. Okay? In other words, this is a hydration of an element. So the hydration actually follows the same kind of process as the hydrogen halide addition, except that here, rather than a chlorine, you are adding an OH. So you can see that almost any alkene can undergo Now, when you want to add water, typically the reagent that will be used is a 50% aqueous acid. And most commonly we use sulfuric acid, it's H2O, 50%, H2SO4, 50%. This mixture will add, again, it goes through the same process where the predominantly the H would go to the carbon containing the maximum number of hydrogen. Therefore, it is going to be added here, and the OH would be added to the other one. So, so this is the major product. And of course, we can predict the minor product where the OH will be added here, but that's actually very, very small amount, more than 80% of this product. Because it follows through the same process where the acid, or in this case H3O plus, will be added, so the double bond picks up the proton from here and generates the more stable cation. And that's the one undergoes attack by water. Which would form a protonated species. And then this extra proton will be picked up by another molecule of water, giving you the final product. This is the tissue product. Now, it is now relevant to also discuss another thing. Remember in the previous chapter, you learned that you can start with an alcohol and you can make an alkene from that. And in fact, we use sulfuric acid to make that. Remember? But we talked about you can take this alcohol sulfuric acid, and that is going to generate the alkene, where this is the alpha carbon. Remember, you have 3 different beta carbons, and all of them can generate a product. Nevertheless, the major product will be formed according to Zaitsev rule, which would be this one. Right? And that's the one we started with. So this is really the 2 reactions going from forward to backward or backward to forward, depending on which direction you're going. Right? You remember this reaction we discussed before, and now we're showing the reverse reaction. Now, which one would really go? It really depends on one important thing, because in the previous reaction we used concentrated sulfuric acid, and in this reaction we use an aqueous sulfuric acid, which is 50% sulfuric acid, 50% water. And that brings us to another important issue in organic chemistry that relates to the microscopic reversibility of reactions, where you can manipulate the reaction depending on what you are doing. In this case, the important component is water. Okay, so alkene, you add a molecule of water, and then you can get alcohol. And the fact that water appears on the left side of this equation, okay, indicates that if you go forward, you generate the alcohol. If you go in the reverse direction, you actually take away a water molecule from the alcohol. And that, how you manipulate, is actually predicted a long time ago by a French chemist called Laurent Chatelier. Who suggested that a system at equilibrium will adjust when stress is applied to it. And in this particular context now, what it means is the stress is in the form of water. Okay. If you use concentrated sulfuric acid, water will take taken out. If you use a dilute with a lot of water, this is going to go in the other direction, make the alcohol. Okay. And so that's consistent with the Chatellier's principle that in equilibrium you can actually go back and forth depending on how you're doing. So from an alkene, you want to add 50% sulfuric acid with water and go to the alcohol. And when you want the alcohol to dehydrate and generate the alkene, you actually use concentrated sulfuric acid with very little water. So that allows you to manipulate reactions. And in fact, we often manipulate reactions this way because at equilibrium, the reaction stops, not quite stops, but the definition of equilibrium is that if you are going from, let's say, reactant to product, and at equilibrium, when the equilibrium is reached, the equal number of molecules going from left to right and right to left. So they kind of cancel each other, even though the reaction don't totally ever stops. So therefore, it allows you to, for example, in another reaction, if water is produced, then if you remove the water, then the reaction will again continue to go on. And that is again, even though this is telling you qualitatively, there are also measurements that you can make quantitatively to do that. And in order to do that, one particular term that I will introduce you is the free energy of a reaction, also known as Gibbs free energy. Which is given a symbol G. So, what does the G tell you? Because what the Gibbs free energy tells you is that you can quantitatively actually calculate, depending on the exact conditions of the system, whether the reaction will go from forward to backward, or from left to right, or right to left. And you can essentially calculate that. So the way we measure is actually by delta G, where you have G products minus G of reactants. And delta G should be negative if you want the reaction to go from left to right. So from reactant to product. So delta G is negative when the reaction is favorable. Delta G is 0 when equilibrium is reached. And the way to calculate that is in the following manner. Let's look at a reaction that you have. The lowercase letters indicate the number. So, certain number of molecule A, you react it with certain number of molecule B. That gives you certain number of molecule C and certain number of molecule D. So, this is a general expression of a reaction and indicating all the stoichiometry. And in that case now, we can also define a delta G0 as a superscript, which indicates that this is the Gibbs free energy of a standard system. By standard, I mean when you have a system that is under 1 atmospheric pressure, and let's say if it is solid. If it is liquid, then it's actually 1 normal or 1 molar solution in water. So that's a standard system. And the relationship of delta G0 with delta G is in the following way: delta C0 plus RT ln the products divided by the reactants So this is the expression that we can define. R is the gas constant and T is the temperature in Kelvin. Now, when in equilibrium, delta G becomes 0, right? At equilibrium, therefore, the expression actually goes to delta Z0 can be defined as by transposing its minus RT ln. And this is the entire thing is the rate constant. K. So we can define that this way. And so it also allows you in a standard condition to figure out all of this. And I won't ask you to apply that, measuring the calculations, but the general idea is important for a better understanding of the processes. Because one thing I think is important to recognize is, again, look at the reverse reaction of, let's say, an alkene, such as ethylene, in the gaseous form, plus hydrogen, also in gas, going to ethane. Now, when we look at this reaction, okay, again, these expressions of delta G allows us to figure out how we can manipulate this reaction. Because sometimes you want this reaction to do the addition, sometimes you want it to do elimination, take out the hydrogen and form the alkene. How can you do that? If you measure the delta G values of these systems, then you will be able to figure this out. And another important relationship between them is that you can express the delta G as delta H0 minus P delta S0. So these are all standard expressions. This is the Gibbs free energy. This is the enthalpy content, something that we already have used several times in terms of hydrogenation and other things. And this is the entropy part. Okay? So entropy is the randomness of the system. So entropy actually, going from left to right, is unfavorable because you're generating from two systems, one system. So the entropy is actually reduced. So that from left to right, if you look at this arrow, the entropy factor is negative. And normally, the enthalpy, as we have learned by hydrogenation of the alkenes, that the heat is released. So the enthalpy is also negative. Delta H is also negative when you are looking at the reaction from left to right. And obviously it would be reverse. It would be positive when you are going in the other direction. If you're looking at the reverse arrow, the delta S is positive and delta H is also positive. Now, the important thing is that you have a subtraction sign in front of this. And that allows you to manipulate this reaction because at low temperature, or pretty much a wide range of temperature, these delta H will be the dominating factor. And that is going to carry out the reaction from left to right. You do the addition, and essentially significant heat is released, and therefore this reaction will go from left to right. But at a very high temperature, you can actually do the reverse reaction where hydrogen will be taken out and you will form alkene. So greater than 750 degrees, what happens is this expression becomes fairly large, and even though the delta H0 is positive, this gets so large that overall it's still a negative number. And therefore the delta G0 is negative, and therefore it's favorable to go from right to left. So this would be reverse reaction is favorable. And typically, when the reaction, just like, remember we mentioned that exothermic and endothermic, that relates to the delta H. delta H is negative, the reaction is endothermic. Similar expressions are also used with respect to the Gibbs free energy. Delta G is, sorry, this is the other way around. Delta G is negative. Delta H is negative. That is, the reaction is exothermic, and this is positive. Then it's likewise, delta G is negative, which is the favorable process. The reaction is exergonic. And if it is positive, then it's endergonic. And even though the delta H component is very important, that can be essentially changed based on the temperature used in the whole process. So you can manipulate the reaction accordingly. Did you understand what I was talking about? Yeah. Okay, that means a similar, it is a term given just like exothermic and endothermic. That exergonic is a favorable reaction. Okay. And endergonic actually needs energy to be provided to the system in order to carry out the reaction. Okay. So I'm going to talk about thermodynamics at this point because I want to ask you to make any calculations, but this general idea of how we can manipulate the reaction using thermodynamics is very important. All right, so the next reaction is that you get addition of water molecule, but what if you I indicated that you add water by aqueous acid, which is going to go through a carbocation, and then will add based on whichever is the more stable carbocation form, right? So it follows the Marconi upstream. What if you want the product by the anti-Marconi, which is a minor product and therefore difficult to prepare? So there are chemical method that has been developed over the years in order to create the anti-Marconi product. And one of the best way to do that is hydroboration oxidation reaction. The hydroboration oxidation reaction essentially uses a diborate or similar kind of salt. Diborate is B2H6 or other boron compounds. So in this process, what you do, let's say, let's take a simple alkene. And obviously, if you use this one with aqueous acid, the hydrogen is going to go to this carbon, and the OH is going to go to this one, right, according to Marconi. And by using diborane, what is done is we add B2H6 and use a high boiling solvent, diline, a solvent is used. And in this first reaction, therefore, what happens is that the boron adds on to generated in the very first step. And then you hydrolyze that with hydrogen peroxide and a base. And by the process, essentially generate CH3, CH2, CH2OH. So this process therefore involves two steps, but it gives you the anti-Markovnikov product. First step is reaction with boron diboron in the dilime solvent. Sometimes tetrahydrofluoride is also used. And then the second step, you use hydrogen peroxide and base to hydrolyze that complex and form the corresponding alcohol. Now, in addition to being anti-Markovnikov, this reaction have the H and OH are added in the scene orientation. Okay, they come from the same side. And therefore, wherever, in this particular case, there is no stereochemistry involved because you can rotate it freely. But let's say if you have a 6-member ring system and so if you have this compound and you carry out the diboron reaction, the first step B2H6 in dilime, and then the second step H2O2 and OH minus. What you are going to get is not only that you are going to get the OH added here in this carbon, but also their H and OH would come from the same place. So you form the H, OH, so the added system is this one, and they're coming from the same place. And so they will have a very distinct stereochemistry involved in there. In other words, in this case, the OH and the methyl group would be on the opposite side. Their relationship would be friends. Okay. So this is where I will stop today. I will continue. There are several other reactions.